here in Palma de Mallorca, and that you learn a lot during the PERSEO summer school. A few practicalities, I'm sure Angelo and will tell you. Basically, the building is very well located because just if you turn to the left, over the bridge, you find quite a lot of bars and cafes and everything for coffees and lunches and dinner. And also just, on that big avenue, there are also coffee bars and restaurants and everything. And just here in this corridor, you got the first is the toilet for men, and the toilet for women is at the far end of this corridor. Okay. So, like I said, welcome to the OAB. I hope you have a great time and you learn a lot. And that's me.
Thank you. Frank and I are the theoretical organizers. So this is the theory. Yeah. This is the practice. So, in addition to Alessandra supporting, of course, the whole network, Raul and Meiji have been doing all the preparation and everything. So we have to thank them. Alessandra, you want to say something?
No, I hope you enjoy, you learn a lot. This is a great opportunity for everyone, and it's for me to please thank one host and the organizer. So enjoy, and of course everyone, included not the PERSEO, should sign as a speaker. That would be really grateful for your presence here. So I'll leave the sheet around in a minute.
Thank you.
So
Thank
much.
you. And for external students,
Yes.
Are you here? Is there any non-PERSEO students here?
Yeah.
So you are an external student, and you, the only one?
No, she's
Her.
also-
So do you want to say who you are, so that the other people will know you? Briefly, your name, where you come from, why you are here.
Currently working on the topic of robotics. So now I have my PhD in technical development. So there's a chance to come here, know people who work in the same area, and
Thank you. We will talk to you. Thank you. Can I please ask the ESRs? The ESRs are the Marie Curie students in our network. The ESRs, to make sure you include the external people in the community. I know you are very well amalgamated. So when you organize tonight partying, dancing, if you don't want to invite the supervisors, fair enough. But you need to invite the local people, the local students. And then there will be
Also because Andrew, it's
when today. So we are celebrating their birthday. So what day is today? The 20th of September. Very good. Any other business? Anything that you want to ask? Why we hope that Michael connected.
Yes, he's on.
Very good. Okay, so oh no, we have 2 more minutes. So hi, Michael. Where are you? Ah, there you are. Anything you want to ask? So coffee break will be outside when you enter the patio. And is the audio working from your computer? So then okay, thank you, guys. Okay.
You text before.
Just
So Michael, can you hear me? Can you talk, Michael, to make sure we can hear you? We don't hear you. Michael, are you speaking?
We can hear you.
We can hear you. Very good, very good. So I'm going to introduce you, Michael.
So now you should be able to hear me, right?
Yes, very good, very good. So I'm going to introduce first Michael, and then he will give us a talk. So if you say cloud robotics, especially AI, robotics, and cloud, you really mean Michael Beetz. So we are very lucky that he accepted to be the speaker. He couldn't be with us for other commitments, but it's a nice start to the conference to have the person who connects the cloud. In particular, you will see the AI, artificial intelligence side of robot learning and robot communication and so on. And this will be also a nice start to all the different aspects of cloud robotics we are going to look at during the summer school, including towards the end, technical aspects of securities. But let's start from AI and robotics, which is at the center of it. Okay, Michael, you have, I think it's 1 hour, including questions. So Michael, at 50 minutes, we will try to stop you if you keep talking, or we will try to leave some space for questions.
Cool.
Thank you.
Thanks a lot for having me, and I'm very sorry that I couldn't come to Mallorca, but it turned out that we have our school, PhD school, exactly in the same week. And so just for you to see, so these are the t-shirts of our school. And yeah, so today I want to talk a little bit about robotics, personal robotics, where I think kind of the big issues are in getting personal robots out, and in particular also what we need to do in order to get the computational power, the cognitive capability into the end systems, and how we can actually support that by having infrastructure that is shared by robots and that you can have off board, right? So, I mean, if you look at personal robots, so for me, going that step from an autonomous robot that acts in a world to having a personal robot that basically works together with a human, right, is a huge step, right? So because if you have an autonomous robot, the robot can act as it likes, right? So it kind of what matters is that the task is achieved. If you have a robot that actually has to do tasks together with a human, right? So the human and the robot, they have to have a shared understanding of the task. They have to have a shared understanding of the environment, and also kind of about what they can do and how they do it, right? And I think this is actually a huge step for robotics to come at a point where the robots kind of come in an environment, look into it, and they are able to answer questions about the environment in the same way as humans are, right? And if you're thinking about what to get into the cloud and what to have on the individual robots, right? So the way I think about the problem that you want to have something like a Siri agent in the cloud, right? Kind of a system that you can ask questions, right? But you need an infrastructure on the robot where you are able to ground the kind of the knowledge that you get from somewhere else, so at least kind of part of it. And you have to make it apply to your camera image, right? And somehow you also, if you do knowledge-based inferences, you have to get answers that are given in the abstract, translate into the body motions of the robot, right? And if you're thinking about personal robotics, right? So everybody has in these future roadmaps kind of many visions about where these personal robots can help assist people and what kind of tasks they can do, right? And if you look at that problem from our community point of view, right? So there are many different environments. We can have personal robots in a hospital, in people's home, at the workplace, and the environments will be extremely different, right? And the tasks that the robots perform will also be a huge variety. And we will have very, very different forms of robots. Some will be more like an Alexa on wheels. Others will be sophisticated and manipulate in our environment. And we as software engineers and researchers in AI, we have the problems that we kind of have for each combination of tasks, robot and environment. In the worst case, write a computer program that does the job on the robot, right? And if we are writing basically a robot control program for each of these combination, there is no way that our community and the whole software industry can deliver the number of different programs kind of that are needed, right? So, and if you're looking at that problem, so what we need is a revolutionary way of programming personal robots, right? And not only personal robots, it's robots in general, but I think the situation is even worse for personal robots, right? And if you look at the evolution of life, right, so there's supposedly one point where it's called the Cambrian explosion, and where nature discovered sight and vision essentially as a new mechanism, right? And now the different species could hunt and they could mate and something like that. And because evolution has found that new way, right? So kind of the number of different species exploded, right? And so we need the same kind of thing in robotics. So that's kind of a case that was made by Jill Brett. And I guess many in our community, and probably also a large number sitting in the room, believe that we have that kind of revolutionary technique, and that's deep learning. And because if you're doing things by deep learning, you don't have to program at all, right? You just throw data at your system. You are looking at your computer program as an end-to-end system. And if we are getting enough data where we basically can learn a function from object, task, environment, and context into the robot behavior and into the body motion of the robot that should be performed in that point, right? So then we can approximate a function that does the job, right? And I think the community in deep learning is pushing that in a vehement way. And it's a case that this technology is a huge step forward, but it's in no way that this technology is actually sufficient for the kind of robots that we need to get into the world and get running. And that this is a case, right? So you can see on many different examples, right? So you kind of a robot that is using a large language model and that is trained with all the text in the World Wide Web, right? And if there is spilled red wine on your favorite carpet in your room, the robot might go on and take a vacuum cleaner in order to clean it up, because I think there are enough commercials in the web that suggest that a certain vacuum cleaner can clean everything, right? And so the point is not whether kind of the robot does that wrong in that specific situation, right? But the problem with learning end-to-end from data into behavior is that the system does have no means to actually check whether kind of that inference that is made on data and patterns in data makes actually sense in the world and could work, right? And the same happens if you're thinking about actions you have never done before, right? So if you as a human, so I could tell you about an action that I'm going to pour coffee into my mug at the bottom of the ocean, right? And this is certainly an action that we cannot get experience data for, right? But still, we as human can actually answer questions about this made-up action, and I think for me, this is actually, if we want to have these capabilities, we need to make models of actions and create them and then reason about them, right? Again, if everything is kind of correlation of data and mapping patterns in data, and that kind of thing is not possible, right? So I think there is a way that we can actually manage the complexity in building all these systems, but that revolutionary technique is rather the combination of generalized knowledge, generalized programs, and machine learning, right? And again, I refer to Jill Bratt's seminal article where he said, robots are already making large strides in their abilities, but as the generalizable knowledge representation problem is addressed, the growth of robot capabilities will begin in earnest and will likely to be explosive, right? So let me then just, it's always helpful to think about the problem before you present the solution. So if we are looking at personal robots together with humans, deploying them in homes, I think that one of the most essential, probably the most essential problem that we have to do is we have to write control programs that are able to map underdetermined manipulation task requests. So something like set the table, bring me something to drink, give me a coffee, and map that in a specific body motion of the robot that achieves the desired effects and avoids unwanted ones, right? And this is actually a huge gap for building a mapping, because if you're looking at it, there are so many things missing. Something like set the table. And the system has to have a lot of knowledge to actually accomplish such a task, right? So kind of, if you bring something to drink, you have to at least infer that kind of something to drink is a substance. So you cannot carry a substance on its own. You have to put it into a container. You have to manipulate the container and so on. So it's kind of a huge problem that we are seeing here. And we have to invent computer programs that solve this huge problem in a very, very broad context, right? At least ideally. So let me just give you an example. And this is a robot setting the table. The robot is just performing a loop, and in each loop, it again performs a highly underdetermined task request, namely kind of get the next item that is missing on the table and put it at the right place on the table, right? And we can see that computer program.
And I'm a PhD student at the Institute for AI at the University of Bremen. In this video, the PRT is performing the household marathon demo of the EASE project. The idea of the demo is that the robot executes different variations of mobile pick and place, whereby it needs to act completely autonomously with a minimal amount of human interference. The first task is to set a table for cereal breakfast for one person. This involves 5 objects: a bowl, a spoon, a cup, some milk, and a box of cereal, which have to be brought to the dining table. Afterwards, the table has to be cleaned up, so the washable objects are placed into the dishwasher, the cereal box is placed back into its storage location, and the milk box is thrown away into the trash as it's assumed to be empty. The perception system that we use is called Robotics. It employs an ensemble of experts approach based on the principle of unstructured information management. Importantly, it works in assumption-free scenes, which means, for example, that we don't expect a supporting plane to exist for each object. This is required, for example, for the objects in the dishwasher or in the door of the fridge. The motion control framework that we use is called Organised. It does whole body control. For the PR2, this means that we control the arms, the torso, the base, and the head simultaneously. It uses a constraint and optimization-based approach with which we can define multiple goals at the same time. For example, grasp the object while looking at your hand, staying away from the joint limits and avoiding collisions with the environment. The plan executive that we use is called CRAM. It uses the reactive planning approach such that the plans concurrently perform the motions and monitor their execution. Simply put, this means that if a failure happens, such as an object slips from the gripper, the robot reacts immediately. The sequence of actions and the failure handling strategies are engineered according to a general model of mobile pick and place, and the parameters of actions are inferred at runtime by querying the knowledge base. There are a lot of challenges that need to be solved in order to master these mobile pick and place actions. First, the robot needs to have an enormous amount of knowledge about its environment, the task, its own capabilities, the user preferences, the physics of the world, and common sense rules. Second, the robot needs to be able to execute its actions in a wide range of variations. For table setting, this means that it should be able to get any object from any location in the environment and place it at any other plausible location. The robot also has to deal with the non-determinism and the partial observability of the world, which simply put means that acting in the real world very often leads to failures, and the robot needs to be able to recover from them. And it needs to keep its beliefs about the world in a consistent state, as close to the state of the real world as possible. Finally, in order to reach human-level skill and mastery, the robot needs to be able to improve its performance over time based on collective experience. For more information, please follow the links in the description.
So this is a complexity of the problem when we are looking, and this is a case where we didn't have even a human present when the robot was actually acting in the environment, right? So imagine how much more complicated everything goes is when a human is around, right? And the robot has to make sure that the human sees the robot when it's manipulating, and that it has to have eye contact with the robot, with the human in the right moments and everything, right? So it's kind of, I think we just have to acknowledge the complexity and the depth of the problems that we have to solve if we want to get the personal robots out. So we are trying to push and kind of, and I think it's kind of an area that it has huge promise, right? But we are also at the very beginning of actually exploring that, right? And I think science research always starts with experiments, and if your target problem that you want to solve is intelligent agency, right, then the experiment that you have to do is to write a robot control program that exhibits kind of intelligent agency for one specific instance, right? And we have to develop many different robot control programs with different methodological approaches, right? And I'm just presenting one of them, and that's kind of the way we look at the problem, right? So as we have seen, the most general problem is mapping underdetermined task requests into a specific body motion. As I've hinted, so we are decomposing the problem or specializing the problem in a manner that we want to use generalized action plans. So we believe that things like fetching objects and placing them, pouring, cutting, that they have common templates of behaviors. They also have common knowledge that is applicable, and that we want to actually represent that explicitly, right? It's also, at the end, it's the body motion that matters, right? So the only thing a robot can do is actually giving voltages to the motors in its joints and move its body, right? But we have to find kind of temporal patterns of these voltages that actually achieve the right effects and avoid unwanted side effects. And again, we want to represent that as a motion plan. Then we need a cognitive process that is capable of mapping the generalized action plans in these specific motion plans. And the cognitive process that does the job is we call contextualization. So this process takes knowledge and reasoning in order to take a very specific task request in a very specific situation, and it takes the generalized action plans, specialize them in a specific motion plan, and this is kind of what we want to solve. And I just stepped through to give you an intuition of how such a thing could be achieved. So let's first look at that generalized action plan we have seen in the video, right? So, and this is in a nutshell how that that plan looks, right? So when we fetch and place an object and a destination, so we can have various description of objects and destinations, and this fetch and place plan is supposed to get any object from any place to any destination, right? And the way the plan is organized is that it's consisting of 2 steps. And at the first step, it's the robot has to be at a location where the object it's supposed to be pick up is visible and reachable. At this location, it has to perform an action, namely fetching the object. And then at the destination, it has to do kind of the analogous thing for placing the object. So it has to be at the location where the destination is visible and reachable, and then it places the object. So what we are doing is we allow a lot of hand waving because we are not specifying kind of where the location is. We are not specifying how the fetching operation has to be done, but we assume that the knowledge that is needed in order to do these things are provided through the contextualization step, right? And there's another thing that is important about having kind of a plan that looks like that. And this is, we want the robot to be able to understand what they are doing. So they have to be able to look at their own plans, look at the structure and say, what they are doing, and the other thing is we want to do reprogramming, right? So the robot should self-program itself in order to make things more efficient, to be more cautious, or to incorporate an advice of a human. So we want to make the self-programming task of the robot as easy as possible. And we are, I guess, most of us are computer scientists. We know that high-level programming languages are made for that, that we basically have to design our programs that they are highly modular, that we are using data abstractions, control abstraction that mirror essentially the structure of the task we want to solve. And yeah, by basically representing the action in such a modular way, you make the task of the robot in terms of introspective reasoning, in terms of self-programming easier, right? So then we take that generalized plan and we couple it to a knowledge base. So we have general knowledge chunks. So something like cups used for table setting have to be clean and unused. Cups in the cupboard are usually clean. Cups have to be grasped from the outside. But there can be much more powerful knowledge chunks. So it can be something like you always should parameterize your motions to avoid unwanted side effects. Spilling is an unwanted side effect, right? And or we can have something like that can be learned from experience, the pose to pick up a heavy pot. So the point is of having such knowledge bases, which basically are composed of modular and general knowledge chunks, is that kind of these individual knowledge chunks, they are in general true. So we have to be kind of more cautious here, but the idea is that they are modular knowledge pieces, and they are useful in many contexts, right? And in particular, they are applicable in contexts that the robot doesn't know yet, right? So they are actually the mechanisms that let the robots deal with open worlds and basically enable the robot to accomplish tasks it has never done before, right? Because it can compose these general knowledge bases and basically apply them to a new task. So that's kind of the game that we want to play, right? So if you're looking at personal robotics, what we would want is we want to equip the robots with these generalized plans, and we would like to have a general knowledge base that is shared by robots, where robots actually learn and contribute kind of knowledge to that generalized knowledge base, which could, for example, be in the cloud, and we have to be more careful to kind of reflect privacy policy and ownership of data, but kind of I think the general idea is you want a community which is donating knowledge to the community of robots, and in order that robots can develop something like common sense, right? Okay, the second component of our plan is a motion plan, right? And again, so I think the proper way to look at how tasks like fetching and placing objects should be done is looking at humans. So we are looking into cognitive psychology, see what kinds of models of human reaching and placing are made in these areas. So we use the model of Flanagan, which essentially decomposes fetch and place into these four motion phases. kind of cognitive psychology look at action, behaviors and actions and try to study them. So they are not actually interested in generating the motions. And if you have a generative system, you have to often go kind of in at a more detailed level, right, where you specify things. So we basically extend that model from cognitive psychology in a way that it can describe the behaviors of the robot that we need for accomplishing these tasks, and we want to make the relevant parameters of each of these phases explicit so that the robot can set them, right? And as you have seen in the video, the kind of the motion plan we are using is sufficient for opening the drawers, kind of cupboards, getting things out, closing them. So actually the model we have here is pretty general in terms of scope. And so what you in general want, if you have these robots acting together with humans, right, and a human gives the robot the task, pour the water out, and you have a pot with potatoes and water in it. So the robot has to infer things like grasp the pot by the handle, hold the pot horizontally, tilt the pot around the axis between the handles, hold the lid while pouring. If the robot cannot infer these kind of components or constraints on the body motion, there is no way that we can have robot control systems that could actually, in the variety of situations and tasks that we have in human-robot companion settings, kind of reach the required generality that we need, right? So just let me step through how then the thing is done. So we get in, and there is an underdetermined task request, something like the robot has to execute an action of the type fetch and place. The object is a cup, and the location, the destination should be the kitchen table, right? It should be put on the kitchen table. So the robot has to infer that kind of the cup has to be clean and unused, not used by somebody else at the moment. So kind of the thing that we are doing is we are selecting the generalized motion plan, taking the task request and expanding the plan with the motion plan and all the parameters of the motion plan. So such as which arm is used, how it should be grasped, and so on, right? And then kind of the step comes where all the intelligence lies in, because we want to know what the parameter settings for all the variables in the motion plan are that actually ensure that the action we want to execute will be successful, right? And that's kind of the most essential inference task that any robot has to do, right? It's the question of how do I have to move my body in order to achieve my goals. So for me, the biggest question is the knowledge of the robot, right? So if we are looking at many of today's robots, and if they look with a camera on a scene and what they extract in terms of information out of the camera image, it's kind of back to kind of problem we want to solve, right? So we want to accomplish doing the right action in all conceivable contexts, right? And so for me, one of the big questions is, how is it possible that we can represent enough of the environment of the current situation in the belief state of the robot, such that this context-dependent behavior is possible, right? And I think there are two representation structures which are very essential for these tasks. And one is, how do we represent the situation, the current state of the environment? The second question is, how do we represent the activity that is going on, right? And it's not enough to essentially have representations of that, but these representations that we have of the state of the environment and the activity that is going on has to be machine understandable and machine interpretable, right? So we want to actually cast these representations as a knowledge base that you can ask, kind of like a Siri agent, and then your reasoning system is able to extract the answers out of the situation and what has happened so far, right? And that's has to be, for me, kind of the general direction we have to go. And so the way we are approaching it is, so for us, I think the only representational structure that I can imagine that where we have a belief state of sufficient expressive power is actually the virtual scene, the scene graph representations of virtual reality environments, right? If you think of the scene graph representation of virtual environments, right? So you have the agent that is acting in the world, right? So you have photorealistic representations of the world that that you act in. You have rendering mechanisms that you can generate basically the images that the robot expects to see during its actions, right? And this is very important because this is actually the point where we want to ground the knowledge into the robot control system. And the second place where we want to ground the knowledge is the motion, right? So the robot knows what body motion it executes or should execute. And it is basically sending the signals to its motor, and then that changes the environment. Again, the virtual reality environment, they come with simulation environments, which are actually the computation mechanisms for doing that. And the second data structure is just, you want to interpret what is happening in this in this perception action loop, and you want to record it as an ongoing activity. Okay, so how are we going to do that, right? So the idea is that we basically build representations of environments as virtual reality scene graphs. So here you see on the upper right that essentially the different object parts, they have particular colors, distinct colors, and that means that for every object part with a different color, we also have an identity of the object, and we can kind of link that to the knowledge base, right? We can talk about everything that has a distinct color in that scene, right? And that's kind of very cool, right? And it's a very complex belief state, right? But we know from virtual reality technology that these very complex kind of representations of the world, they can be updated in real time, right? And if you have graphic cards and something like that, but the whole game industry works on making these things feasible, right? So yeah, so what we want to have is digital twins as an implementation basis for knowledge representation and reasoning. And it's kind of a cool data structure. It has rendering and simulation mechanisms, and this gives us a lot of cognitive capability we need for human-robot interaction, right? And yeah, and it's so cool because the scene graph data structure gives us access to all kind of the data pieces we need of a very complex environment around us. Yeah. So we can also make these digital twins machine understandable. For that, we define ontologies, right? We are defining the concepts and order them in taxonomies. We can also define the individual concepts such as Wikipedia defines them, but we define these concepts in terms of a logic knowledge base, right? So that the system can infer that. And if we are now going on and say that basically one piece of data structure in our virtual reality scene graph basically has a certain ID, we can say that this is an instance of a concept in our huge taxonomy, right? And by doing that, the system can inherit all the knowledge that is contained in our encyclopedic knowledge base and apply it to something that it can see, right? So it's kind of a very, very strong idea. So, and then you kind of just want to go ahead and define all the concepts that there are in a way like Wikipedia does it. So fluids have density, viscosity, temperature, surface tension, and we have simulators for that, and so on. And that is all knowledge that you need in order to determine how to carry a tray with bowls, where the bowls also have maybe some fluid inside, right? And as I said, so the other thing is that is very cool is that these virtual reality scene graphs are virtual knowledge base. So how powerful that idea is, you can imagine when looking at this slide, right? So you can have logical predicates, something like the expected image, right? And we basically define that logical relation in terms of procedural attachments, right? So the expected image is if we take the virtual camera in our scene graph representation, place it at exactly the same pose where the robot believes its camera pose is, and then we are rendering an image with the parameters of the camera, and this gives you essentially the image that the robot should see, right? Kind of a second very powerful predicate is which object is actually depicted at a certain pixel in your image, right? And again, so this predicate can be made operational because we are rendering each object part in a distinct color. So the object identity is just a mapping from the color into the name area, right? And we can also do things like give me a segmentation of the milk box by defining that all other objects besides the milk box are invisible, and then we are putting the rendering engine and we render the image. So the important thing here is that this gives us actually a way of grounding the knowledge we have in the perception system, right? So and the idea is you're taking your belief state. Your belief state is essentially represented as a virtual reality scene graph. You say render it, and if what you're rendering, your belief state, actually corresponds to what you see with your camera, you can make the assumption that your belief state is right, and that you can operate, you can parameterize your actions based on this belief state, right? And yeah, and so yeah, just kind of the next step is essentially the actions and the action episodes that are happening. So now we are in a very good position because we have represented the situations that we have in a very powerful representational framework that is very detailed, that matches the perception capabilities of the robot. And because we have kind of this infrastructure, but we also have the simulators inside the virtual reality systems, so we can also kind of take the systems and let them listen to the events that are happening in the simulation system and already kind of interpret that these events when they are happening, right? So what you want to do is kind of, if you're a robot and you're in an environment and acting with a human, you essentially want to place the human that you are seeing in your own belief state in the virtual reality environment, kind of replicate kind of the motions that you see the human doing in the simulation environment, and use the simulation environment and the predictions and everything else that the simulation environment gives you in order to make sense out of the situation. So this is very similar to the simulation theory of cognition, right? So, and then, so this is kind of how it's happening then, right? A human is doing cleaning the table, putting things in the dishwasher, right? Because we are in the simulation engines, we are getting the force dynamic events, the events that allow us to pass activities, such as the contact of the hand with an object, whether the object is supported by a supporting surface, and so on. And if we are doing that, we can basically segment actions into tokens, because everything is machine interpretable, right? So already at the passing time, we can build kind of models that match our cognitive science model of the action, the Flanagan model, and we can already ask here questions about the ongoing interpreted activity and ask the system to, for instance, visualize the trajectory, right? So you have a parser that actually makes sense out of the activities that the robot sees somebody else doing, right? And you want to push actually getting these interactions as close to reality as possible, but that's kind of just playing around with ideas. And but again, the important thing is, so if you are looking at that environment, this environment is actually a symbolic knowledge base. So you can load, like we do here, a symbolic knowledge base, a prologue knowledge base. And when we load that, kind of, we can completely reconstruct the environment that we are acting in, right? And because it's a prologue knowledge base, we can ask prologue queries about the environment, because kind of we made the environment machine understandable. So we can ask questions like, give me all the handles of electrical devices, and it basically gives you the handle of the fridge and of the oven, right? And all the handles, all the containers, all the objects, the hands, the body parts, and everything else, right? So that's kind of the way we envision to get the robot aware of enough of the environment so that it can actually interact with humans in a meaningful way. And here you see actually how it's passing the action of getting the milk box onto the table, and it's segmenting it into the different motion phases. And now we are actually in a model that is rich enough to see whether the human has some tremor and kind of weak or anything else, and we can actually push the cognitive capabilities of the robot, right? And we do that in all kinds of things. We do that with gaze, with trajectories. And as you can imagine, if you get all these data and you can extract these data from these episodic memories, right? So then you can learn from experience, you can learn about how to actually interact in a more kind of competent way with humans, right? Okay, so let's see. I'm skipping some of the things. So just want to get two things, because we are also talking about cloud. What do we get in the cloud, and where should we do the computations, right? So, and I just want to give an outlook at some of the ideas that we have and where we want to push things, right? So if you think about human-robot interaction and have these kind of research actually be driven by a community, also in a manner that the community can build synergies and work together on these problems, right? So there are certain obstacles why this is not possible, right? So at the moment, right? I think the first one is there are very few teams that actually can accomplish manipulation tasks in a manner that is so general as in the video we have shown, right? And it's kind of clear because it's a huge barrier that you build systems that have the perceptual capabilities to do that have the knowledge and reasoning capabilities to do that have the motion control capabilities to do that. And I think to do that, you need kind of very good robots. You need a big team. Kind of the big team has to work together. And I think it's only possible at some places, right? So for one thing, we would like as a community to have access to kind of an infrastructure to robots with these control systems that have a basic capability to doing that, right? The second thing is we want to have models of these environments, of these robots and everything else, because models allow us to work scientifically in that, and then we need, again, the humans in the code. So, okay. So what we are trying to do is we try to build a laboratory along these ideas. So we built our environment as a virtual reality environment that is photorealistic, right? And but at the same time, this virtual reality environment is a knowledge base where you could basically answer questions about all that you see in the image, right? Then you want to have the robot, like in our video, acting in that environment, right? So we need some basis where we can show whatever our research results are, they actually work embodied in a computer program, right? And you also want to have a simulation environment, right? And so and this is because we only have very few physical labs where this work can be done, right? But we would actually like to enable to actually work with these control programs and give access to that kind of technology, right?
Michael, 2 minutes left. 3
But,
minutes left.
pardon?
1 minute left.
I didn't get sorry. What
5 minutes, Michael.
Oh, okay. I just try to finish that up. Yeah. Yeah. So and then you basically have your whole knowledge representation and infrastructure to study with that, right? And you get your whole learning infrastructure, you get the data out of that. You want to basically store the data accessible, if it's possible, to the community. You want to have data processing infrastructures for doing that. So in our case, we are doing that through OpenEase. So people can actually work on these episodic memories, ask questions in terms of logic queries, and then the system answers, right? But if you're looking at the episode, and this is extremely important, the episodes can be reproduced, right? So in the data, there's enough information that we can replicate the scenario we've recorded, and we also have all the semantics that is needed in order to make it machine understandable. And the big thing is you then want to do it you want to realize that as a Docker environment that you can actually download, and you can basically run the complete lab remotely at your place in order to do research. And you also want to couple it with an interactive learning environment for cognitive robotics, where basically also you have books for cognitive robotics that are Jupyter notebooks, and where you basically can have access to these remote labs from the textbook out, right? And that's, I guess, yeah, so that's kind of the vision we have in order to push that forward. And I conclude here. Yeah, so I'm ready for questions. Yeah.
Thank you, Michael. We have time for 1 or 2. We have 4 minutes, so time for some questions. If you want to ask a question, maybe it's best if you come here or say it loud. Come here, it's better. Can you hear us? I hope.
Yes, yes.
Thank you.
So Michael, thank you for your presentation. I had a question regarding your knowledge base. How are you planning to include deformable objects? Like in a kitchen, we might have objects that change their shape along time, let's say like an apple. Is there a plan towards type of manipulation?
Yes, yes. So we are working on that. So I think it's you want to look. So we are taking 2 examples at the moment. One is pouring, and one is cutting, right? So you're looking at scene graph representation and simulation models, where you can basically have cutting as a specific simulator, right? And so that simulator actually makes sure that when you are traversing an object with a knife, that you get 2 pieces, and the pieces are there where you have contact, right? I think again the big thing and the high effort thing is developing simulators for these physical interactions, and yeah, and I hope that again in a generalized setting that we do not need too many different simulators, right? So we have Newton physics, we have something like Flex for fluids, we need these for cutting, and we need it for some other things, but the hope would be not too many, right?
Thank you. Thank you. Any other questions? Yeah, Joanna? We'll try the microphone.
Hello, Michael. You have seen my notes on the relevance of hardware tool.
Sorry, I can't hear that.
He doesn't get that.
Hello, can you hear me now?
Yes, now it's good. Yeah, thanks.
Okay, so a great talk, by the way. So my question is, it's very interesting how you create an encyclopedic knowledge base and how you represent the environment for the robot to get all the data that it needs. But how do you connect the knowledge base with the generalized action plan? For example, in a particular context, how does the robot know which information it needs to get from this knowledge base to execute, for example, fetching a cup? The cup has to be unused and clean, and it might be in the cupboard. How does the robot know all the sequence of information that it needs to combine together to get that action?
So kind of the hypothesis is that the pattern of the action, the high-level pattern, is general, right? And which also makes sense because humans act very stereotypically, right? And this is also to minimize the need for explicit communication, right? So we already see when somebody is doing something. So I think these general patterns are deep in human behavior, and that we have them to keep things computationally feasible, right? And yeah, so one of the hopes is that these patterns are there, and this is I think mainly kind of it's not that all actions have to have these structures. It's just if agents adapt to these structures, all the knowledge gets applicable and they can share it. And I think it has a lot to do with common sense, right? So if you combine these patterns with common sense, you get a lot of variability that you need to act in the real world, right? And we have to understand how these two work together.
Okay. Yeah, thank you.
Thank you, Michael. Thank you. I think we stop here. Thanks for the participation online, and good luck with the rest of the activities.
Yeah, thanks a lot for having me, and sorry that I couldn't be there in person. Yeah.
Thank you.